Last video I proved a formula which described the acceleration of a particle traveling in a circular orbit, and I proved mathematically through a lot of maths that the acceleration of a particle traveling in a circular orbit can be described in two main components, the tangential direction and the normal direction, and it will have in the tangential direction the acceleration will have a magnitude of v dot, and in the normal direction facing towards the inward of curvature it will have a magnitude of v squared on r, where v was actually just the magnitude of your velocity at any particular time t, or your speed. And for the sake of completeness, I figured I should probably put this in here too. I also wanted to say that the acceleration of a particle traveling in any particular type of path can be described as its acceleration in its x component plus the acceleration in its y component. And that's just for R2. But to complete our library, I figured it was probably worthwhile talking about polar coordinates and perhaps coming up with a formula to describe not just the circular path, but any particular type of path. So bear with me and I'll go through the maths to try and prove a particular formula which is really useful in physics. So let's say we've got an x and y coordinate system just here, y and x. And let's say we've got a particular arbitrary path. It could be anything. It could be a runner running across a football field at some particular time t, and this is just the path he makes. But let's say we've got that particular path, and let's say that we wanted to describe the position of our runner at some particular time t using a vector. So let's say we wanted to create a vector just here, and let's call that vector r of t, and it's a vector. And let's say that vector has a magnitude of r. So in other words, the distance of this vector from here to here is going to be r. And I really wanted to specify that r is not a radius in this particular case. It's just a distance vector. But most textbooks use little r and big R, so I kind of wanted to stick to that type of notation. That way I wouldn't confuse you guys. Ironically enough. All right, so let's get started. Now we've got the basics of our coordinates. Let's just finish off defining a few things, and then we can fully get started. So let's define one more thing. Let's define theta as being the angle made from the positive x-axis to our vector r, just here. And notice that it's a function of time, and in fact all of these are functions of time, right? Because they all change when depending on the time of the particle. Like the particle could be here at this point, but maybe later it could be up here, meaning that r, theta, and r are all different. So that's why they're functions of time. Now let's also talk about unit vectors. Let's create a new type of unit vector. So let's say we've got a new unit vector. I'm going to call it ER. And it's a unit vector, so it's going to have a magnitude of 1. But I've defined it such that it's in the same direction of our distance vector just here. And I'm also going to define a new unit vector, E theta, which is also got a magnitude of 1 because it's a unit vector, but it's also going to be perpendicular to ER. Alright, let's describe these unit vectors a little bit using mathematics, and then we can get started on polar coordinates all the way. So let's just zoom up on that particular point of contact just here, and we've got one unit vector just here, ER, and we've got one unit vector just here, E theta, and we've got our two other unit vectors. Oops. We've got our two other unit vectors, J and I. Don't forget that all these vectors have a magnitude of 1 because they're unit vectors. And we also know that this is going to be theta. So basically, let me tell you about what I'm doing just here. Basically, this is just a combination of all the different unit vectors. Because they're vectors, they don't actually have a starting position, right? I mean, you can place them anywhere, and I've decided to place them all with their tails just facing just here. That way I can mathematically describe them as a function of I and j. So bear with me a little bit. Maybe you'll get this, hopefully. So ER is going to be equal to whatever it is in the I direction plus whatever it is in the j direction. Well, it's going to be equal to 1 cosine theta and 1 sine theta, right? 1 sine theta. I'm basically describing this in I and j at the moment. So ER has a component in the I direction of 1 cosine theta and the j direction is a component of 1 sine theta. Don't forget that that's because this is a magnitude of 1 just there. The hypotenuse is 1. Alright, let's now describe E theta. E theta is going to be equal to what? Well, if I were to draw a triangle down here, an imaginary triangle just here, we know that this angle right here is going to be 90 minus theta, which means that this one's going to be theta using geometry. So we know that it's going to be expressed in terms of I and j, and in the I component it's going to be negative because it's facing the other way, and it's going to be equal to 1 minus 1 sine theta. And in the j direction, it's going to be equal to positive 1 cosine theta, because it's in the direction of the j. All good. Okay, so that's E and R and E and theta all described in terms of I and j, and you'll see why that'll come in handy later. It may seem a little bit arbitrary at the moment, but I think you'll see where it'll fit in sooner or later. So now let's try and describe R in terms of our unit vectors that we've just created. Well, we know that R, our distance vector to our particle at any time t, is going to be equal to the magnitude of our vector, which is also a function of time, I should add, times by our unit vector, ER hat. Alright, I mean, this should kind of make sense to you at the moment, right? I mean, our distance vector is going to be equal to the magnitude of our distance vector times by the unit vector in the direction of our distance vector, right? So this is true. This is important right here. This describes our position of our particle just in terms of this unit vector just here. Not only that, but we can also now differentiate both sides with respect to time to find our velocity. Remember that our velocity of our particle is just the derivative of our position of our particle with respect to time. So we know that our velocity vector, which is a function of time, I should add, is just going to be the derivative of our position vector with respect to time. Alright, now that we know that, we can just differentiate this equation to figure out what our velocity vector is. Well, that would imply that our velocity vector will be equal to the derivative of whatever RTER hat is, right? It's just going to be the derivative of RT ER hat, right? Don't forget that every one of these terms inside this bracket is actually a function of time here. Just imagine that later on this path, as this runner's running along here or something like that, let's say he reaches this particular point here. ER is going to be in a different direction. It's going to be a different unit vector, so it's a function of time. It varies with respect to time, which means that you can't treat it as a constant, which means that you'll also have to derive it when you're taking the derivative. So to do this, we use the chain rule, and we know that's just going to be dr dt times ER hat plus R times whatever the derivative of ER hat is. We don't know what it is yet. That's why I'm just going to leave it as the derivative of ER hat. Right? So don't be confused here. I've just used the chain rule from this step to this step. Nothing too fancy. And let's see if we can take a minor detour here to figure out what the derivative of our unit vector in our R direction is. Well, in order to find that out, we just need to derive this thing just here, this beast. Well, let's derive that beast now. What is the derivative? What is the derivative of ER hat? Well, we know when it's expressed in I and j components, we can just derive each of the individual components. So that's just going to be equal to the derivative of cosine theta, which is just going to be equal to minus d theta dt sine theta. And its j component will be the derivative of sine theta, which is just going to be positive d theta dt cosine theta. Alright. What do we notice about this? Well, if we were to factor out a negative d theta dt, sorry, if we were to factor out a positive d theta dt, we get minus sine theta and cosine theta in the brackets, which is this thing right here, isn't it? That's just going to be equal to, well, I'll write it out for you, minus sine theta, cosine theta, which is just going to be equal to theta dot, I'll just draw a dot there, it'll save writing d theta dt all the time, times by e theta hat, right? So that just means that this is just going to be equal to dt, der dt. So using this now, I'll even write it out for you guys, dt er hat. Alright, that's that. That's an important formula right there. So let's just replace that with this now that we've figured out what it is. That's just going to be equal to r dot. Once again, I'm just going to use r dot to denote dr dt times by er hat, our unit vector in our r direction, plus r times by, and we discovered before it was just going to be theta dot e hat theta. Is that right? Is that what I wrote down here? Theta dot e, yep, that's it. Alright, so now we've got our acceleration of our particle at any particular time t. Already we've got a result just here. Already this is a result. In other words, our velocity of our particle at any particular time t can be expressed in our er direction, which is going to be r dot, the magnitude of your distance vector differentiated with respect to time, and it's going to have a component in e theta direction, which is going to be r times theta dot. Alright, so that's one result already. Let's differentiate it one more time, and bear with me because the math will get a little bit hairy. We're going to differentiate one more time to just get our acceleration of our particular particle. Well, we know our acceleration is going to be equal to the derivative of whatever this is. Well, that's just going to be equal to, well, the differential of whatever this is. So I'll draw an arrow just here. The differential of whatever that is, I'll put d dt, which is going to be equal to r double dot er plus r dot d dt er plus, so basically I've differentiated this beast, this little term here, and it turns into this, plus the differential of whatever this is when differentiated. So I'm just differentiating the right hand side. I hope I'm not confusing you using this strange notation just here. Plus whatever this term is, which is just going to be equal to the derivative of whatever this beast is, which is just going to be r dot times, and once again I'm just using the chain rule, r dot theta dot e hat theta plus r times by whatever the differential of this beast is here, times ddt of theta dot e hat theta. So let me just draw an arrow just there so you totally know what I mean. There we go. Cool. Alright, so basically this term just here derives into this term just here. Cool. Alright, now we've almost finished. We just need to fully evaluate what our acceleration is, and we're done. So at is going to be equal to r double dot er plus r dot times what's d dt of er? Well, we already figured out previously it was just theta dot e theta, theta dot e theta plus, well, it's now I'm just going to add this term. It's just going to be r dot theta dot e theta hat plus r times whatever the derivative of this is right here. Well, we can use the chain rule again within the chain rule to get e double dot e theta plus theta dot times whatever the derivative is of e theta hat. Alright, so now in order to do this we now need to figure out a new thing. What's the derivative of our unit vector in the theta direction? What is d dt of e theta hat? Well, we know that we can simply just derive it with respect to time, because we figured out what it was in the x and y coordinates. So that's just going to be equal to minus theta dot cosine theta. And that's just going to be, and the y component is just going to be equal to minus theta dot sine theta. Sine theta. Alright. So, we're almost done now. Let's figure out what this is. Well, if we factor out a negative theta dot, we can get negative theta dot times by cosine theta, sine theta just here. And that becomes minus theta dot times by what's cosine theta sine theta? That's just ER, isn't it? So it's just this one right here. So that's just going to be equal to minus theta dot ER, where ER is just your unit vector just there. So minus theta dot ER. That's how these two derivatives are related to each other. Alright, so that means we can replace this with that. So if I were to write down the acceleration vector again, in fact, let me just copy it because I'm running out of space here. Let me just copy this piece just here. Bam. Alright. I'm just going to copy this down here because I was running out of space. Alright. Done. Cool. Alright. So if we were to rewrite that out now, we just get the acceleration of our particle at any particular time, expressed as a vector, is going to be equal to r double dot er hat plus r dot theta dot e theta hat. I'm just simplifying this right now. Plus r dot theta dot e theta hat. I just realized that these two could be added together because they've got the same units, but I'll do that in the next step. Plus r, I'm just expanding the brackets right now, r theta double dot e theta hat plus theta dot r times whatever the derivative of e theta is, which we figured out was just minus theta dot er hat. Well, now just doing the simplification one line lower, our acceleration vector is just going to be equal to, well, let's group all the ERs together. We're going to have r double dot. Let's see, anything else is a function of ER? Well, this is just here, so that's just going to be minus theta dot squared r. And that's just going to be all times by ER hat. Now let's also group the all the coefficients of E theta hat, which is just going to be the sum of these two. Which is just going to be 2 times r dot theta dot plus, well, this is also multiplied by E theta, so that's just going to be plus r theta double dot right here. And that's going to be multiplied by our unit vector, E theta hat. Alright. Alright, let me just highlight that in green just here to signify its importance. So, we've got our acceleration can be described in both our unit vectors in terms of ER and E theta, and this is exactly it, where r is the magnitude of our distance from our origin, which is also a function of time, and theta is just going to be our angle from our positive x-axis towards our distance vector, which is also a function of time here. So this is just this is useful. This is the acceleration which describes any differential path.